Let's talk about solving falling object problems using differential equations. For objects like dust or aerosols or snowflakes, that is tiny objects, the force of air resistance is directly proportional to the velocity v of t. But generally, the force of air resistance is directly proportional to the velocity squared, v of t squared. Many textbooks will claim that the force of air resistance for large objects is directly proportional to the velocity v of t, but this is grossly inaccurate. That's according to an interesting article by Lyle Long and Howard Weiss, The Velocity Dependence of Aerodynamic Drag, a primer for mathematicians. So I'm going to focus on snow because it would be unrealistic to assume that the force of air resistance is directly proportional to the velocity if we're dealing with huge objects like a baseball or a buffalo or whatever. Suppose a snowflake with a mass of 3 milligrams, that's 0.000003 kilograms, falls from a cloud that is 3,200 meters high. Let x of t represent the distance the object has fallen in t seconds. Notice x of t is not the height, it's not the position, it's the distance fallen. Assume that the force of air resistance is directly proportional to the velocity v of t, and that the proportionality constant b is 1.5 times 10 to the negative fifth Newton seconds per meter. Find an initial value problem involving v. We need an equation involving v and dv dt. We can get that by analyzing the forces at work on the falling snowflake. And those two forces, we're going to keep it simple, are gravity and air resistance. Recall that Newton's second law of motion is F equals ma. Okay, so we have F equals ma. The force due to gravity is going to be m times acceleration due to gravity, g. That's m times 9.81, so we have 9.81 m, 9.81 times the mass. The force of air resistance is directly proportional to the velocity v. So this force is going to be bv, that's 1.5 times 10 to the negative fifth v. The total force working on the snowflake is F equals 9.81 m minus 1.5 times 10 to the negative fifth v. Now notice, we want negative 1.5 times 10 to the negative fifth v and not positive 1.5 times 10 to the negative fifth v. That's because air resistance is hindering movement. It's working against gravity. So if this is the force of gravity and this is the force of air resistance, they need to have opposite signs. Air resistance is hindering the work of gravity for a falling object. Okay, so this is F. We're going to replace F with ma. That's why we're working with forces. We can replace it with ma. And now let's divide both sides by m. We get a equals 9.81 minus 1.5 times 10 to the negative fifth v over m. Let's represent a as dv dt. Again, we have 9.81 minus 1.5 times 10 to the negative fifth v over 3 times 10 to the negative sixth. This simplifies dramatically. This is just going to be 5. Okay, so we have 9.81 minus 5v. The initial velocity is 0 meters per second, so the initial value of v is just going to be v of 0 equals 0. After all, the snowflakes are just dropping. Nobody's throwing them down. So this is our initial value problem. Find an equation for the velocity v of t of the object by solving the initial value problem. Okay? This is a first order linear ODE, ordinary differential equation, because it is of the form dy dt plus p of ty equals q of t. We do need to rewrite it, so we need to get this thing on the other side. Okay, when we do that, we have dv dt plus 5v equals 9.81, and v of 0 equals 0. Awesome. So to solve this linear first-order differential equation, multiply both sides by e to the integral of p of t, and then we're going to get this. Okay, and why do we do this? We've seen that earlier. The left side is now the derivative with respect to t of y e to the p of t. E to the integral of p of t is called an integrating factor. It enables us to integrate the left side. Okay, so this is what we want our differential equation to look like. We integrate both sides with respect to t. This is what we get. The left side simplifies dramatically. It's just y e to the integral p of t. And the right side looks like this. And you just hope that that right side is integrable. It's got to be integral. It's a textbook problem. It's got to be integrable. Okay, so this is what our differential equation looks like. Ours is dv dt plus 5v equals 9.81, v of 0 equals 0. So we can see that this p of t is just plain 5. And again, we're working with v, V is our, V is the variable, not y. Okay, so P of t is 5. So the integrating factor is e to the integral P of t. That is, in other words, e to the 5 dt, which is just e to the 5t. So multiply both sides by that. So we take this equation, we multiply both sides by e to the 5t, and this is what we end up with. Now we integrate. So we end up with this hairy mess over here, but again, remember that this left side is just going to be y e to the integral P of t dt. In this case, that's v e to the 5t. And the right side's pretty easy. The integral of 9.81 e to the 5t dt is 9.81 e to the 5t over 5. We don't need the plus. We're going to throw in the plus c over here after we simplify this. So this is 1.962 e to the 5t plus c. Let's divide both sides by e to the 5t. We end up with this. The e to the 5t's cancel, and we're just left with v equals 1.962 plus c over e to the 5t, or simply 1.962 plus c e to the negative 5t. Okay, now to find c, we plug in t equals 0 because we know what v of 0 is. Plug in t equals 0, get v of 0 equals 1.962 plus c e to the negative 5 times 0. That's just going to simplify to c e to the 0, which is just plain c. So 1.962 plus c equals 0. Thus, c equals negative 1.962. So the velocity v of t is 1.962 minus 1.962 e to the negative 5t. Find an equation for the motion x of t of the object. Again, x of t is not the height. It's not really the position. It's really the distance fallen. So here's our formula for v of t. Let's just integrate both sides because the position x of t is the integral of v of t. So we integrate v of t. This again was our v of t. We saw that earlier. And we end up with x of t equals 1.962t minus 1.962 e to the negative 5t over 5, or negative 5. In other words, that's 1.962t plus 0.3924 e to the negative 5t plus some constant. Don't want to reuse c, so we'll call this one c1. Okay, so this is our formula for x of t. So we know x of 0 equals 0 because the distance traveled, that's x of t, the distance traveled by time t equals 0 is 0, because at time t equals 0, it hasn't gone anywhere. So x of 0, plug in t equals 0, and this equation is now going to look like this. Okay, that simplifies to 0 plus 0.3924 times 1 plus c1. In other words, it's 0.3924 plus c1, and that equals 0 because x of 0 equals 0. So our c1 is negative 0.3924. That means when we plug this in, we end up with x of t equals 1.962t plus 0.3924 times e to the negative 5t minus 0.3924. Determine when the object will strike the ground. Bam! It's a snowflake. It's not going to make a sound like that. So this is our formula for x of t. We want to know when it's traveled 3,200 meters because, again, x of t is the distance traveled. The cloud is 3,200 meters above the ground, so we want to know when x of t is 3,200. So we just solve this. You can just solve this on your graphing calculator, solve this equation, and you end up with t is about 1,631 seconds, which is roughly 27 minutes. We've simplified this model. It's probably going to take longer, maybe more like an hour, because there are certain things we've ignored. We've ignored the updraft, and we could take into account horizontal movements of the snowflake, but yeah, we ignored that. By the way, the snowiest place on Earth is Paradise Ranger Station in Mount Rainier National Park in Washington State, which averages about 600 inches of snow per year. That's 50 feet of snow per year.